All right, friends, welcome back. Happy Friday. This is the last of 3 lectures. Let's see, some of you have been asking what we're going to get to before the end. I think it will take us today and Monday to get through chapter 28 and maybe even a little bit beyond that. If we do anything in any of the remaining chapters, it'll be on Wednesday. It'll be about polymers. There won't be any new mechanisms, and I'll basically just be showing you, taking you on a tour through the wide and marvelous world of plastics and dental composite and Kevlar, so that you can get a sense for what polymers are. All right, let's go ahead and begin. Last time we were talking about the Suzuki reaction. This is the reaction of a vinyl, or rather an aryl halide with either an aryl or vinyl boronic ester. And the kind of bond that we're making is a bond between two sp2 hybridized carbons. You've got one that's aryl in this case, and the other is vinyl, but the purple one could also be a benzene ring. So the catalyst that we use is this palladium 0 species. It starts out as palladium tetrakis triphenylphosphine. And right now, you can tell it's palladium 0 because these are all L ligands that leave as neutral molecules. That means palladium itself is neutral because there's no charge on the complex. Palladium comes with 10 valence electrons, so that's a D10 metal. And if you count overall 10 on palladium and 2, 4, 6, 8 from the ligands, this thing already has 18 electrons. We call that coordinatively saturated. That means the valence shell is full. This is like a noble gas configuration. So there's no chemistry that can happen yet. The catalysis can't happen yet until a couple of those ligands dissociate. Removal of 2 of those phosphine ligands gives you still a palladium 0 species, still D10, but now there's only 2 L ligands, so it's a 14 electron complex. Now there's room for other stuff. So the oxidative addition step, as we talked about last time, is a pair of electrons from palladium. 2 of those D electrons form a new bond with carbon, and then the electrons in the bond between carbon and halide form a new bond between halide and palladium. Once that's done, both of those bonds belong to their respective X ligands. Both of those pairs of electrons belong to those X ligands. So palladium has formally lost 2 electrons, and that's why we call this an oxidative addition step. If you count these electrons as belonging to the X ligands, the palladium has 8 d electrons instead of 10. If you reflect on the fact that this is neutral, and both of these are X-type ligands that would leave as negatively charged, palladium has to have a +2 charge, so that now gives us the palladium 2 species. Next, we're going to swap out the vinyl portion of the boronic ester for the halide, or we're going to swap out the halide for the vinyl portion of the boronic ester or acid. So this is literally just a handoff between ligands between boron and palladium. Bromine leaves and makes a new bond with boron, and then the vinyl ligand gets transferred directly to palladium. Nothing changes in oxidation state. This is just a ligand swap. We call it transmetallation because we're thinking of both palladium. Palladium is a metal. Boron is an honorary metal. I don't know. So they're trading ligands. The vinyl ligand ends up on the palladium, but we haven't changed palladium's oxidation state. When you have these 2 carbon X-type ligands close to each other, then electrons can come from one of the carbon-palladium bonds and attack the other sp2 carbon and then electrons in the carbon-palladium bond there can go back onto the metal. That releases our product and takes you back to your starting catalyst, which is again a D10 palladium 0 species. And so this catalytic cycle turns, and it can turn over many, many, many times. So you only need a fraction of a percent of your starting materials. A fraction of the percent of those can be the palladium catalyst. All right, questions about that catalytic cycle? Go ahead.
Does it need to be an aryl and a vinyl, or can it be 2 aryls, 2 vinyls?
Can it be 2 vinyls? No, in general, and I don't know why, but it can be 2 aryls. So an example of 2 aryls would be this reaction, which I think we talked about a little bit last time. You have this aryl halide, this aryl boronic ester, and you can make the bond quite easily between the 2 benzene rings. And so far, this is the only way that we've learned this year how to make a bond directly between benzene rings. So here's the vinyl, or I'm sorry, the aryl halide portion, and here's the aryl boronic ester portion. Yeah?
Is there a reason why the stereochemistry of that bonds
Is there a reason why the stereochemistry, if it's a vinyl halide, yeah, the stereochemistry is preserved. I think because you never have a free carbanion. A vinyl carbanion is a little bit interesting. It would basically be like this. It would basically be sort of SP hybridized, and you could imagine losing stereochemistry, but you never really have that. It's sort of a direct handoff. That's hand waving, I don't exactly know, but you can think of it that way. Okay, what else? All right. There are, for synthesis kind of questions, it's good to have an idea of where you can get these reagents from. The aryl halide you can get very easily from benzene using electrophilic aromatic substitution, right? That's the aryl bromination reaction that we learned early on this semester. If you want the aryl boronic ester, you still need this, but you convert it to the organolithium reagent, and then you use this boron reagent. It's only got 3 groups on it, so there's still an empty p orbital there. The electrons in this carbon-lithium bond attack the boron to give you this sp3 hybridized boron species that's negatively charged. To avoid that negative charge, one of the methoxy groups leave, and that gives you your boronic ester with your aryl group attached. And this is the carbon that you're going to make the new bond with. If you want a vinyl boronic ester, then the method of choice is to start with this alkyne and then do hydroboration. So this is a revisit of a reaction from 351. It's a syn addition of hydrogen and boron across one of these pi bonds. The hydrogen ends up on the more substituted carbon. The boron ends up on the less substituted carbon. They are added on the same side. And what that means is the boron is always trans to the R group. If you wanted to make a Suzuki reagent in which the boron was cis to the R group, you'd have to use a different method, and I don't think I know how to do that. All right, so one interesting thing to think about is that this bond between 2 arenes has some interesting stereochemical properties, which we're not going to talk about, but basically those orthohydrogens bump into each other. So this ring system is not planar. In fact, they have to twist out of plane and basically be sort of perpendicular to each other to avoid those steric problems. That introduces the possibility for something called axial chirality, which we are not going to worry about. But it is out there, so if you ever hear about it. But just understand when you see two benzene rings linked together directly, it's not flat, they're twisted. And that twisting can have some important consequences. So this reaction is used all over the place in pharmaceutical chemistry to make drug molecules because it's highly efficient and you can run it on a kilogram scale. So you don't have to write any of this down. I just want to show you an example of something in industry that's made via a Suzuki reaction. So you get a sense of the tolerance of the Suzuki reaction to different functional groups. Here is the key bi-aryl linkage. That means two arenes attached directly to each other. And then the rest of it's a little bit weird. This is a molecule that was involved in phase 3 clinical trials for, it's a beta secretase inhibitor, and beta secretase is the protease that clips off the amyloid beta peptide from the amyloid amyloid peptide precursor, APP protein. And of course, amyloid beta is associated with aggregates of amyloid beta are found in the brains of Alzheimer's patients. And so inhibiting that process was thought to be a useful therapeutic strategy. That whole thing is controversial. You can read all about it. But for right now, just accept the fact that this is a drug candidate called lanabecestat. I don't know where they come up with these things. Usually focus groups, actually. They try to come up with a name that sounds cool and scientifically, but doesn't sound scary or gross. And this was developed by the AstraZeneca. So that's a drug company. I think it's British, but they have places in the United States. In any case, here is the key bond. And they were able to make this from the corresponding starting materials. They made the boronic ester on the side of the pyridine ring. And there's a little bit more to it than that, but that's sort of where I'll leave it. Here is the alkyne. And then the other reactive partner was just this portion with a halide here. And these are the two carbons that they linked together. They were able to do this with a catalytic amount of palladium 0. They needed some base, they needed to cook it, but 100 kilogram scale. So just so you know, the typical types of chemistry that we do in the fume hoods on the 4th floor in the organic area, at most we'll be making a gram or 2, and that's even usually highly unusual. So 100 kilos is like an astronomical amount. And the fact that this reaction works both in the fume hood on a small scale and then in the chemical industry in a big reactor on a massive scale is really impressive. Also, the functional group tolerance, notice you've got this amino group here. It's adjacent to a benzene ring, but you don't have to protect it to do the reaction. It doesn't interfere. And so this is a very useful reaction in drug discovery. The biphenyl or biaryl linkages are found all over, and it's a really great way to do what's called diversity-oriented synthesis, where suppose you have 10 different boronic acids and 10 different aryl halides. You can easily generate 100 new compounds with only 20 different starting materials because of this coupling reaction. Did we just lose a light? Suddenly it got dark out there. Okay, that's the Suzuki reaction. Let's now talk about the Heck reaction, named after Professor Heck, but fun to say. Ah, heck, yeah. Right. Well, then you're a better person than me, because sometimes when I'm upset, the word heck is not the one I choose. It's probably the one I should choose, but okay, the Heck reaction. I'm going to give you an example of the reaction, then we'll talk about the catalytic cycle. Oops. No, that's fine. So as with the Suzuki reaction, you're going to have one reactive partner that's a halide. And in the Heck reaction, this can be an aryl halide, or it could also be a vinyl halide. So I'll give you a couple of different examples. Then the other partner tends to be a monosubstituted olefin. And in general, Z tends to equal an electron withdrawing group. And the reason for that you'll see in a little bit. So you have option of either of those two starting materials. What you put in the reaction flask is palladium acetate. That's a source of palladium-2. Though it turns out palladium-2 is not the active catalytic species. You also need an equivalent of base, and then you need a phosphine ligand. And the phosphine ligand of choice for the Heck reaction is one in which you have 3 of these. It's like triphenylphosphine, but you add a methyl group at the orthocarbon of all of the phenyl groups. I'm going to just abbreviate this as PR3. Your text will call this orthotoluol phosphine. Triorthotoluol phosphine, but that just refers to this arene on the phosphine. I should point out that there's a huge area of phosphine ligand chemistry. Anybody that wants to do palladium chemistry or chemistry with other transition metals has found in many cases that the identity of the ligand can influence the course of the reaction. And so there's a lot of folks that will try tons of different phosphine ligands. If you want to just see, Google phosphine ligands and Sigma Aldrich, which is a chemical company, and there'll be hundreds and hundreds of different phosphines you could use. And they have different uses. We're not going to worry about the identity of the phosphine ligand. The key is that you make a bond between the sp2 carbon of the aryl halide and the terminal carbon, what we're going to call carbon 1 of the olefin. And the stereochemistry that you get as you make this new bond is always trans. You always get the E stereochemistry. And so that's going to be explained by the mechanism as well. And that's not necessarily obvious because unlike the Suzuki reaction where we had a functional group here that was involved in the coupling, we just have 2 hydrogens on that terminal carbon. So that's the real new thing, difference between Suzuki and the Heck reaction. In the Suzuki reaction, if you wanted to couple a vinyl carbon, you needed a boronic ester. But for the Heck reaction, one of your reactive partners can be this monosubstituted olefin, no boron necessary. So you don't need something a little bit perhaps easier to access these materials than the boronic esters. The new bond that you make is this one, and the stereochemistry is trans. So if we were to do this for the vinyl halide, we would get, sorry, I just put Z here. Here is the carbon from the vinyl halide, and here is the carbon from the olefin, and the configuration of the new bond with respect to the pi bond on the olefin is E. Now be careful, because some of you are going to memorize, okay, in the Heck reaction you always get trans stereochemistry, and then you're going to do something that doesn't happen. So the stereochemistry on the side of the vinyl halide is preserved. If you do this reaction with that monosubstituted olefin, you do not get this product. Stereochemistry on the side of the vinyl halide doesn't change. It's stereochemistry with the new monosubstituted olefin that is always E. Okay, this one stays the same. You got that? I mean, don't make that mistake. I've just discovered a really easy question I can write on the exam where I switch the stereochemistry up and you fall for it. So I'm warning you now, right? Don't fall for it. Also, these products are dienes. And when you hear a 1,3-diene, you should be thinking, oh boy, Diels-Alder reactions. So one fun way to write a synthesis question might be to have you do a Heck reaction to get the diene and then do a Diels-Alder reaction. So remember that in a Diels-Alder reaction, we have to be in the S-cis conformation. And so you got to keep all the stereochemistry right. Okay, and then if we did a Diels-Alder reaction, I'm not sure what the right dienophile would be, but this is probably a good time for you to review, because in the Diels-Alder reaction, we make a 6-membered cyclohexene ring. The things that are pointing outward in the S-cis conformation of the diene end up on the same side of the new 6-membered ring. The two substituents on the dienophile that are cis to each other end up cis relative to the ring. You get both endo and exo diastereomers and their respective enantiomers. Okay, I'm sorry to remind you of something horrible that you thought you could dismiss indefinitely into the past, but this is one way to combine some chemistry that you know, a diene that you make via the Heck reaction, now incorporated into a larger molecule through the Diels-Alder reaction. That's probably worth a little bit of review. Yeah? Oh, shoot. Stereochemistry. Right. I'm going to, I'll put the E in parentheses to refer to stereochemistry. Is that okay? And this is an electron withdrawing group. My choice of Z was unfortunate. I apologize for that. No stereochemical meaning. For the Heck reaction, you always get E stereochemistry. This would be Z. This is cis. Yeah. I'm sorry about that confusion. Is that good? Okay. Note to self in the future. So I'm going to just write a little choose something other than Z. Well, dear Josh, Z, regards, Josh. Okay. No, sincerely, just regards. Okay, so let's talk mechanism. I want to say that for whatever reason they're using palladium-2 to start with. That's going to get reduced in situ by some of the phosphine ligands. The process is understood. I could draw it out, and I did during the first hour, but it seemed kind of pointless, so I'm not going to do that here. Understand, though, that in the Heck reaction, the palladium-2 is going to get reduced to palladium-0, so that the active catalyst is actually going to be palladium with 2 of those phosphine ligands. So in terms of the active catalyst, it's very similar to the Suzuki reaction. It's a palladium-0 species, all right? Which is why they gave the Nobel Prize to these, Professor Suzuki and Professor Heck, and there was another, but I forget, together, because the chemistry was so related. So let's do the catalytic cycle. Here is the palladium-0 species with the 2 phosphine ligands. And the first step, as with, and I'm just going to use simple starting materials rather than ones that we used above. The first step is an oxidative addition step. So this palladium complex is neutral. Therefore, palladium is a D10 metal in its palladium-0 oxidation state. Overall, though, before the reaction, this complex has 14 electrons, so there's space for something to happen. And the first step is going to be an oxidative addition step. That is, we're going to take 2 electrons from the metal, 2 of those 10d electrons, and make a new bond with the aryl carbon of the benzene ring. At the same time, bromide is going to leave with its electrons and attack the palladium ring. Now, actually, you could push the arrows in the opposite direction. You could have these attacking the bromine and then these attacking the palladium. You can't actually tell which direction it is. That oxidative addition step takes you from palladium-0 to now palladium-2, which will have 8 d electrons. The phosphines are L-type ligands, neutral. The phenyl and the bromo group are X-type ligands, which is how you can tell that this is a palladium-2 complex. Notice that these electrons in the carbon-palladium bond came from palladium, but we don't care. We're counting them as though they belong now to the carbon of the phenyl group. So that's how palladium gets formally oxidized. All right. Also important, if you're keeping track, there are now 16 electrons in this complex. And that's important because for the Heck reaction to work, we're going to need to add one more thing to this complex. There's space for it because we're not yet up to 18 electrons. So the next step we're going to call just olefin binding. We're going to have the pi electrons of the olefin donate as an L-type ligand to the palladium. This is different from the Suzuki reaction. In the Suzuki reaction, we did a transmetallation step to swap out the bromide for the other partner. But recall that in the Heck reaction, we are using an olefin, so there's no boron here. Okay? So we can't do a transmetallation. Instead, we have to have the alkene, the pi electrons of the alkene, coordinate the metal as an L-type ligand. Okay. It's still palladium-2 at this stage. It's still a D8 metal, but this time there are 18 electrons. So we would say that complex is coordinatively saturated, meaning there's not really space for anything else to add to the metal. Okay, anything you want to ask there? Right. Now what happens next is difficult because it's a new kind of step that you haven't seen before. Basically, what we're going to do is we're going to take the electrons from the phenyl group, this X-type ligand, and we're going to make a new bond with carbon 1 of the olefin. You can think of that as the phenyl anion attacking the pi star of the olefin. And so that's one reason why you'd want this to be an electron withdrawing group. If that electron withdrawing group were, for example, some kind of carbonyl, then this is an alpha-beta unsaturated carbonyl compound, and it makes perfect sense for a nucleophile to attack at that carbon. We're going to be general because you don't have to have a carbonyl at that position, but the idea is this withdrawing group makes this olefin electron poor, so a nucleophile can attack here. At the same time as that happens, if you're dumping electrons into a pi star, the pi bond has to break, and those electrons will tend to move over to carbon 2 and then form a new bond between carbon 2 and palladium. This kind of step involves migration of the phenyl group onto the alkene. It also is basically like an insertion of the alkene in between the palladium carbon bond. So the reaction is often called a migratory insertion. And I'll try to be clear about the new bonds that we formed. The new bond between palladium and carbon 2 of the original olefin, and then the new bond between the phenyl group and carbon 1 of the olefin. And oh shoot, incidentally, that bond is the one that we wanted to make in the product. Okay, so we've made that sigma bond. But we don't yet have, but we gave up the pi bond between carbons 1 and 2, and so we're going to have to accommodate that. Oxidation state of the metal did not change. We still have 2 L-type ligands and 2 X-type ligands. It's still palladium 2, there's still 8 d electrons, but there are only 16 electrons in the complex because instead of having 5 things coordinated to the metal, we now only have 4. All right, questions about that step? That one's hard. I always forget exactly what happens in that step, so that one's going to be worth a little bit of practice. Okay, so in our process, remember, we have made now this new sigma bond, but at the expense of this pi bond. So we've got to get the pi bond back. And we have to do so in a way that gives you just the trans stereochemistry. So I'm going to redraw this molecule in a way that reflects the active conformation. Okay, so what is going to happen now is we're going to do something called betahydride elimination. For this reaction to occur, the hydride here, the hydrogen here, really needs to be eclipsed with the palladium. Those two bonds need to be eclipsed. So that if we were to look down this carbon-carbon bond, we would see that the phenyl group is eclipsed with the hydrogen, whereas the hydrogen on carbon, what we've called carbon 1 and carbon 2, the phenyl group on carbon 1 is eclipsed with the hydrogen on 2, the hydrogen on 1 is eclipsed with the Z group on 2. Can you see how it's better? We could rotate around that bond such that hydrogen was here and phenyl group was there, but now you've got a steric problem, right? So in order to avoid that, we rotate around the bond in such a way that we keep the phenyl group as far apart from the Z group as possible. I'm a little bit oversimplifying here, but that's fine. Now, to restore the double bond, if you think about it, we need to take one of these two pairs of electrons in these bonds and make a new pi bond, and then we need the other thing to leave. And what's going to happen is going to be very similar to sort of almost an NAD plus oxidation. Recall in NAD plus, electrons kick down to make a carbonyl, and hydride leaves as a leaving group. Though it's not actually a leaving group, it gets delivered directly to NAD plus. In this case, electrons in the carbon-metal bond will kick down to form the new pi bond. At the same time, hydride will leave but be handed off directly to the palladium. This kind of process is called Betahydride elimination, because it's almost like a E1CB or an E2 reaction where you kick electrons down but your leaving group is H minus. Doing that creates a new pi bond between carbons 1 and carbons 1 and 2, so that your product, the pi bond, is restored, and with trans stereochemistry, but this is the new sigma bond that you made. That's your product. And then what's the fate of the catalyst at that point? Well, now instead of a palladium-carbon bond, you've got a palladium-hydrogen bond. We're still, if you're paying attention to the X ligands, you've still got two. You've still got two L-type ligands. This is still palladium-2. It's still a D8 complex with 14 electrons overall. So, we've made our product, but in order to turn over and start again, we've got to regenerate the palladium-0 starting material. And to facilitate this process, it goes faster when you have a base. You could imagine doing reductive elimination by having hydrogen attack the bromine and these electrons going back on palladium. But it turns out it's faster if you have an equivalent of base, remove the proton from the palladium. Those electrons in the palladium-hydrogen bond go back on to the palladium. That's reduction. If we stopped there, the complex would be negatively charged. So we are going to have palladium, we're going to have bromide leave from the palladium. And that's going to get us back to our starting catalyst. And we're going to make this tetraethyl or triethyl ammonium bromide salt as a byproduct. So this step is called a reductive elimination, but there's also a deprotonation going on. Some people will not show this. Some people will show the reductive elimination to generate HBr, and then afterward they'll show the base deprotonating HBr. Either way is fine. This is what Dr. Michaelis has in his notes, so I am I trust him and I don't know anything, so we're going with that. Okay, that was pretty rough. What questions do you want to ask about the Heck reaction? Yes?
The step where the phenyl group attack the pi star, the alkene,
Yeah.
do we just assume that it will always attack the pi star? Is that something that we're...
Yeah, recall in this step I use the words the phenyl group attacking the pi star to break the pi bond. That's one way to think of it. You don't have to think of it that way. And in fact, it's fine if you don't worry about the orbitals here anyway. Yeah? On the carbon with the Z group, can you have another R group there? That's a great question, and I actually don't know the answer to that. I know you can have, it doesn't have to be unsubstituted at this carbon. I know under some situations you can have another group here.
But it will always be, you always add something to.
For this simple material, yeah, it will always add E. For more complicated cases, I wouldn't ask you to make the prediction. Yeah. Okay, what else? We got to this point in the 9 o'clock class, and then I said, seriously, you don't have any other questions? Because I'm about to unleash new horrors upon you with new reactions, so there's really no attempt to delay me? No? Yeah, toss up, right? You want to minimize your time with the uncomfortable material while limiting your exposure to new material. So there's probably a game theory way of approaching that. Speaking of games, Amber and the boys are coming home from Phoenix. They've been there for spring break because they have a spring break, which is good. Amber's actually in a PhD program here, but she did her work all ahead of time and just skipped class this week, so that's awesome. But anyway, they're coming back today, and so this morning I was running around trying to make it appear in the house, folding laundry and stuff, trying to appear as though I had not been playing video games all week, which I actually had. I have completed the Phantom Menace and Attack of the Clones levels of of Lego Star Wars. I'm just playing through it in story mode yet, so don't judge. I didn't get very many studs and anything, but it was fun, and they've sort of edited it to make it more kid-friendly. Like Jango Fett doesn't really get decapitated, and the Jedi don't really die; they're just sort of laying there. Anyway, it's kind of and Yoda is pretty is pretty awesome in his ability to destroy clone troopers. So that's what I've been doing. Are you jealous? Yes.
Yes.
That's because you have homework and I don't. All right. Other questions about the Heck reaction? Yes. Where the product leaves the palladium, yes. Okay, question? Or you just want to see it? You got it? Okay. What else? Beta, so the two new steps in this process, we've seen oxidative addition and reductive elimination before. The two new mechanistic steps were migratory insertion here, where we basically insert the two carbons of the olefin in between the benzene ring and the palladium. We make a new bond between benzene ring and carbon 1 of the olefin. We make a new bond between carbon 2 of the olefin and palladium, but we lose the pi bond. And then this betahydride elimination step is about restoring the pi bond. I didn't explain why it's called betahydride. That's because the carbon that's adjacent to, that's bonded to palladium is the alpha carbon, and then the other carbon is the beta carbon. So a betahydride elimination. Okay, others? Let's see. Periodically, I get questions. I'm a chemistry professor. I answer questions periodically. I haven't rolled out that one this semester. Most of you have burning questions about the final exam. What should I study? Anything I told you would not be that useful, so I'll try to just be as useful as I can be. You should be current on what we're talking about now, the metabolism stuff and the stuff from 28. If we get to 29, it will be just a little bit. Or if we get to 29 or 30, it'll just be a little bit and not a lot of new reactions, mostly showing you what plastic is. So you should be current on the 27 and 28 stuff. The exam review videos will still be available on YouTube. I think I need to repost the exam 1 video so that you can go back and see what you got wrong on the previous exams on the testing center, and then sort of review. You should also peruse the practice exams. I'm not saying that you should do them all over again, but if you're looking at them and you're seeing something that you're like, I have no recollection that that ever happened or was learned, now's your chance to go back and fix that. Yeah, so that's how I would approach preparing for the final exam. Format will be multiple choice. It is in the testing center at any time during finals week. And what else? Length should be a little bit longer than a 200-point exam because this one counts for 250 points. People have also asked me, do I anticipate there being a curve? What I think people mean when they say a curve is, will the cutoffs posted in the syllabus be more generous than they are? I can't really tell that with any degree of certainty until all the points are in. The cutoffs posted in the syllabus are a hard guarantee. That is, I'm never going to say, oh, guess what? You all did so well on the test that now to get an A, you need to earn a 98. We're not going to do that, right? Because that's just wrong, right? So it will never be more difficult to get an A than earning 93% of the points. I cannot anticipate how much lower than 93% of the points the cutoff will be. I usually round up. Because if I don't, I get emails from all of you making last-minute impassioned pleas and requests, and I figure let's just save ourselves a whole lot of time. But now I shouldn't have disclosed that because now you're going to email me saying, I'm on the verge of being in roundup range. Could you round up anyway? Yeah, go ahead. Will there be a study guide for the final exam? No, though there is a practice exam on the last 2 chapters currently posted on the content page of Learning Suite. Grades, what else? You can sort of pay attention, you can sort of anticipate where cutoffs will move by watching the median or 50th percentile score in the class. If that's in the 80 to 83 range, then that tells you that the cutoff between B minus and C plus is going to be pretty close to 80%. Usually the cutoffs in the upper 50th percentile don't change that much. Usually the cutoff between like C minus and D is substantially lower than 70%. So I realize that's not useful. Once I assign grades, I will put the sort of approximate grading scale, final grading scale on Learning Suite so you can see it. But yeah. Well, next time we're going to learn about how to make 3-membered rings. It's called cyclopropanation, and it will be something out of your nightmare since we hate rings. But we'll see you on Monday.